2.3 is about Venn diagrams and set operations. So the circle graph categorizes America's 55 million Hispanics by the primary language spoken at home. The graph's sectors define 4 sets: the set of U.S. Hispanics who speak Spanish at home, the set of U.S. Hispanics who speak English at home, the set of U.S. Hispanics who speak both Spanish and English at home, and the set of U.S. Hispanics who speak neither Spanish nor English at home. And so you can see the percentage of these 4 sections of U.S. Hispanics and the languages they speak at home in the circle graph. So when discussing sets, it is convenient to refer to a general set that contains all the elements under discussion. This general set is called the universal set. A universal set, symbolized by a capital U, is a set that contains all the elements being considered in a given discussion or problem. Hence, a convenient universal set for the sets described above is U equals the set of U.S. Hispanics. We can obtain a more thorough understanding of sets and their relationship to a universal set by considering diagrams that allow visual displays. Venn diagrams, named for a British logician, John Venn, are used to show the visual relationship among sets. And so in figure 2.4, you can see a Venn diagram. The universal set is represented by a region inside a rectangle. Subsets within the universal set are depicted by circles or sometimes ovals or other shapes. In this Venn diagram, set A is represented by the light blue region inside the circle. The dark blue region represents the set of elements in the universal set that are not in set A. So by combining the regions shown by the light blue shading and the dark blue shading, we get the whole universal set U. Let's use the Venn diagram to determine each of the following sets. And so what is in U, which is the universal set? It's everything that's included in the box. So U would be equal to, remember we use curly braces for sets. We have a square, we have a triangle, we have a money sign, we have M, and we have 5. What is in set A? Set A is what's ever inside that circle that's labeled A. And so we only have 2 elements in A. We have a square, and we have a triangle. Part C asks for the sets of elements in U that are not in A. So everything that's in the square but not inside the circle. And so that would be the money sign, M, and 5. There are a number of different ways to represent 2 subsets of a universal set in a Venn diagram. So to help understand these representations, let's consider the following scenario. You need to determine whether there is sufficient support on campus to have a blood drive. You take a survey to obtain information asking students, would you be willing to donate blood? And would you be willing to help serve a free breakfast to blood donors? Set A represents the set of students willing to donate blood, and set B represents the set of students willing to help serve breakfast to donors. So we have possible survey results like there are no students willing to donate blood or to serve breakfast and vice versa. All students willing to donate blood are willing to serve breakfast. The same students who are willing to donate blood are willing to serve breakfast. And some of the students willing to donate blood are willing to serve breakfast. And so the 4 basic relationships and their visualizations are, the first one being disjoint sets. So that's when 2 sets have no elements in common, and these are disjoint. And so this is represented by two circles that do not overlap. So since set A represents the set of students willing to donate blood, and B is the set of students willing to serve breakfast to donors, the diagram would illustrate that no students willing to donate blood are willing to serve breakfast, and vice versa. The next relationship is a proper subset. So if set A is a proper subset of set B, which means they can't be equal, then all elements of set A are elements of set B. And proper subsets are represented as one circle inside of another circle. So if an X representing an element is placed inside circle A, it automatically falls into circle B. So since set A represents those willing to donate blood and B is willing to serve breakfast, all students willing to donate blood are willing to serve breakfast. So they fall, if they're in one category, they automatically fall into the other one. Relationship 3 would be equal sets. So if A is equal to B, then set A contains exactly the same elements as set B. Equal sets are represented as two sets sharing the same circle. Because all elements in set A are in set B and vice versa. And so since set A are people who are willing to donate and set B are willing to serve breakfast, the same students who are willing to donate blood are willing to serve breakfast. They are interchangeable. And the fourth relationship is sets with some common elements. So in mathematics, the word some means there exists at least one. If set A and set B have at least one element in common, then the circles representing the sets must overlap. Since set A represents the set of students willing to donate blood and B is willing to serve breakfast, some students willing to donate blood are willing to serve breakfast. So maybe not all of them, but there's at least one student who's willing to donate and willing to serve breakfast. And so in the diagram below, you can see the different regions and where these people would fall into the region. So in region 1 would be just our blood donors, but they don't want to serve breakfast. Region 2 would be the people who want to donate blood and serve breakfast. And region 3 would just be the breakfast servers who don't want to donate blood. And down in region number 4 would be the people who don't want to serve breakfast or they don't want to donate blood. So we're going to use the Venn diagram for each of the following sets. So set U, which is everything that's included in all of the regions, 1, 2, 3, and 4. So U is equal. We've got A, B, C, D, E, F, and G. That's every element that's inside my box. Now for what is in set B? That is everything that's in region 2 and 3. That overlapping is still a part of the original set, so you don't want to forget it. So B would actually be D and E. What about the set of elements that are in A but they are not in B? So that is what is strictly in region 1 because you don't want any overlap with B. And so we've got 3 elements. We've got A, B, and C. Everything that's in region 1 and that doesn't overlap into set B would be what is in A but not in B. What about the set of elements in U that are not in B? So that's everything that's in the box except anything that is associated with set B. And so we have A, B, and C. And we also have F and G. What about the set of elements in both A and B? So they have to have A and B in common, which would just be that shared region, region 2, and we only have one element, which is just D. So in arithmetic, we use operations such as addition and multiplication to combine numbers. Now we turn to 3 set operations called the complement, the intersection, and the union. So the complement of a set A, which is symbolized by an A with an apostrophe, is the set of all elements in the universal set that are not in A. And so this idea can be expressed in set builder notation as follows. The set of all x such that x is in the universe and x is not in A. And so you can see in the picture below, it would be that shaded blue region. It's everything in U, but it's outside of that circle A. And so the fastest way to find the complement of A is to cross out the elements in U that are given to be in set A. And then whatever's left over is what the complement of A is. So let U be 1, 2, 3, 4, 5, 6, 7, 8, and 9. And we're going to let A be 1, 3, 4, and 7. So to find the complement, we're going to just cross out all of the elements that are in A and the universal set. So that would be 1, 3, 4, and 7. Everything that's left over is the complement. So 2, 5, 6, 8, and 9. If A and B are sets, we can form a new set consisting of all the elements that are in both A and B, and this is called the intersection. So the intersection of sets A and B, written with this A almost like a cap B, is the set of elements common to both set A and set B. And so let's find each of the following intersections. We got 7, 8, 9, 10, 11, and we got 6, 8, 10, and 12. So what do they have in common? They both have an 8 in common, they both have a 10 in common, and that looks to be about it. And so their intersection would just be 8 and 10. What about 1, 3, 5, 7, 9, and 2, 4, 6, 8? Well, one is odd numbers and one is even numbers, which means they have absolutely nothing in common. And so this would just be the empty set. What about 1, 3, 5, 7, 9 intersect the empty set? Well, the empty set is empty, which means there are no elements, so you can't have anything in common with no elements, and this will just be the empty set as well. Another set that we can form from sets A and B consists of elements that are in both A or B or both. And so we call this the union of two sets. And so the union of sets A and B, written with this A, almost like a U for union B, is the set of elements that are members of set A or of set B or of both. In math, we use the inclusive or, which means it can be in both of them. So let's find each of the following unions. 7, 8, 9, 10, 11, and 6, 8, 10, and 12. So we want to take everything that is written there and put it into one big set. So I'm going to list mine in numerical order. We got 6, 7, 8, 9, 10, 11, and 12. The next one we have is 1, 3, 5, 7, 9, union 2, 4, 6, 8. So we just write everything that is present in our problem. So that would be the numbers 1 through 9. 1, 2, 3, 4, 5, 6, 7, 8, and 9. And the last one, we've got 1, 3, 5, 7, 9, union the empty set. So it can be in either the first set, the second, or both. So we definitely still have the elements from the first set. And then there's nothing to add from the empty set because it's empty. And so we really just get the first set. So the empty set in intersections and unions, if A is a set, then A intersect the empty set is always empty, and A union the empty set will just be the first set of A. So some problems involve more than one set operation. The set notation specifies the order in which we perform these operations. You want to always begin by performing any operations inside the parentheses. So we're still kind of using PEMDAS in a sense. So given that U is 1 through 10, and A is 1, 3, 7, and 9, and B is 3, 7, 8, and 10, we want to find each of the following sets. So we've got A union B, and then we want to find the complement of it. So we have A union B, and then we want to find the complement of it. So the first thing we want to do is find A union B. So we're going to take all of the elements that are present in A and B. And so that's 1, 3, 7, 8, 9, and 10. Now we want to find the complement of that. So if the universal set is 1 through 10, we just want to go through and cross out everything in the set we just found. So that's 1, 3, 7, 8, 9, and 10. And whatever's left over is the complement. So that leaves me with 2, 4, 5, and 6. Now let's do A complement intersect B complement. So we want to find A complement first. So that's all the elements that are in the universal set that are not in A. So this would include 2, 4, 5, 6, 8, and 10. Let's go ahead and find B complement as well. That's 1, 2, and 4, 5, 6, and 9. And now that we've already found the complements, we just want to find the intersection, or what's common to both of these sets. And so we both have a 2, and a 4, and a 5, and a 6. In example 7, we want to use the Venn diagram with some interesting numbers to determine some of the following sets. So A union B, that's everything that's in A and in B. So these are some really funky numbers we use in math. We've got pi, we've got e, square root of 2, square root of negative 1, e to the pi I, we've got 10 to the 100, and we've got this 2 with a funky NO going on. Well, A union B complement would be pretty easy because we already found A union B. And so it's everything outside of those numbers. And there's only one element, and that's 666. For A intersect B, that's what they both have in common at the same time. And so that would be that square root of 2 and the square root of -1. For part D, we're just going to find the complement of the set we just found. So that's everything outside those two numbers. So that would be pi and e to the pi I and 10 to the 100 and 2 to the funky NO and 666. We want to look at A complement intersect B. So first, let's look at A complement. A complement is E pi I, 10 to the 100, 2 to the funky NO, and 666. In B is a square root of 2, square root of -1. For part E, we're looking at A complement intersect B. So let's find A complement first. That's E pi I, 10 to the 100, 2 to the funky NO, and 666. Let's go ahead and write down everything that's in B as well. That's square root of 2, square root of -1, e to the pi I, 10 to the 100, 2 to the NO, and 666. I'm sorry, not 666. And so we want to find what they have in common. They have E pi I in common, they have 10 to the 100 in common, and they have that 2 and O in common. And so those are the elements in the intersection. And the last one, we've got A union B complement. So we know what is an A. We've got pi, we've got E, square root of 2, and square root of -1. And B complement, we've got pi, E, and 666. And so with the union, we just take everything that's present in those two sets, which is pretty close anyway. Pi, E, we got square root of 2, square root of -1, and 666. Set operations and Venn diagrams provide precise ways of organizing, classifying, and describing the vast array of sets and subsets we encounter every day. So let's go ahead and see how this applies to the sets from the beginning of this section. So that was U being the set of U.S. Hispanics. Let S be the set of U.S. Hispanics who speak Spanish at home, and E be the set of U.S. Hispanics who speak English at home. So when describing collections of everyday English, the word or refers to the union of sets. So the U.S. Hispanics who speak English or Spanish at home mean those who speak English or Spanish or both. And the word and refers to intersections of sets. So that would be the people who speak English and Spanish at home. And so we can see the circle graph being translated into a Venn diagram. So we had 43% of people who spoke only Spanish at home. There was 32% who spoke only English at home. And then the people who spoke both Spanish and English at home was 23%. And then the 2% were people who do not speak English or Spanish at home. And so we can find the number of elements in A or B with using that N. It's almost like the cardinality. And so the formula for it is the cardinal number of a union of two sets is the cardinality of A plus the cardinality of B minus the cardinality of the intersection. Because the pieces in that intersection are being double counted, so we have to subtract them off. So some of the results of the Campus Blood Drive survey indicated that 490 students were willing to donate blood. 340 students were willing to help serve a free breakfast to blood donors, and 120 were willing to donate blood and serve breakfast. How many students were willing to donate blood or serve breakfast? So we're going to let A be the set of students willing to donate blood. And we'll let B be the students willing to serve breakfast. And so the cardinality of people willing to donate or serve would be the cardinality of A union B, which is the cardinality of A, plus the cardinality of B, minus the intersection. And so there were 490 people willing to donate blood, and 340 willing to serve breakfast, and there was 120 willing to do both. And so we get 830 minus 120, which gives me a total of 710 students.